it may not be obvious, but noise should have some sort of frequency characteristics. And the easiest way to explain this is by really thinking about a simple example. So let's consider this room. At present, there are 3, 6, 10 men in the room. So do you think that the frequency characteristics of the noise that we collectively make will have a different spectral density than a room full of women? Yes, because our voices are typically deeper, and so the sounds that we generate resonate at a different frequency, okay? So we can define this relationship by what's called the power spectral density. So the power spectral density Vn squared with a bar over it has units of volts squared per hertz, and it is defined as the average power carried by a signal if at a 1 hertz bandwidth around a specific frequency. So I want to be here that we're using the quantity power loosely because power typically isn't measured in volts squared, it's measured in watts. So this is us using the square of an RMS value multiplied by a bandwidth kind of thing here, right? So the power delivered to an arbitrary 1 ohm resistor can be determined by taking the voltage squared. This is a similar situation, okay? Then we will have our spectral density. Which is the square root of our power spectral density measured in volts per square root of hertz. And it is literally defined to be the square root of Vn squared or power spectral density. And then in the frequency domain, we can have an RMS voltage, where our RMS voltage in the frequency domain, V RMS, will be defined as the integral of our power spectral density as a function, let me write that parentheses better, of frequency we integrate over our frequency band of interest, and then we take the square root of this relationship to give us our RMS noise voltage. So now let's talk about power spectral density distributions, okay? So the first one that we're going to deal with is white noise, okay? So white noise is largely independent of frequency. And actually, I've made a subtle mistake here, okay? White noise, by definition, must be independent of frequency. That being said, there are certain things that generate what we call white noise that largely are independent of frequency, but not wholly. So for example, we're going to show in a little bit that a resistor in an electrical circuit behaves like a white noise generator, meaning that it generates noise at a roughly constant spectral density for an extremely wide range of frequencies. But it is not all frequencies. Once we hit the terahertz regime of frequencies, it no longer behaves like a white noise generator because resistors don't generate noise at that frequency. But all the way up from effectively DC through the gigahertz range, which is a pretty large frequency band, it does behave like a white noise generator. So anyway, so white noise is independent of frequency, and its noise spectral density is effectively constant. I'm misspelling effectively. So Vn as a function of frequency is really just some constant value. Graphically, on a spectral density curve, we would have something that looks like this. So here's our magnitude in decibels. Here is frequency measured in hertz. Trying to fill all of that in. This plot here is our power spectral density for white noise, Vn squared bar. Okay. So, because real systems have a finite bandwidth, measured noise is not truly white, but is shaped by the transfer function h as a function of f of a system where measured noise will be defined as the output noise of a system. So let's call this Vn out. This is going to be a power spectral density relationship. Will be the magnitude of our transfer function squared multiplied by our input power spectral density. So for example, if we have a white noise power spectral density being applied to a system whose transfer function is that of, say, a low pass filter, something like this. So let's fill this in. So here's the magnitude of h of f squared. This would yield a measured noise that is the product of these two quantities. Something like this. Vn out squared. Okay. The RMS voltage of white noise is given by the following relationship. The RMS will be equal to the square root of the integral of our transfer function squared times our power spectral density with respect to frequency. And since our power spectral density is effectively constant, we can take that out. And so we would have just our spectral density multiplied by the integral, or excuse me, the square root of the integral of the square of our transfer function with respect to frequency. We can define our noise bandwidth as bandwidth is equal to 1 over the magnitude of h peak squared, where h peak is simply the peak value of our transfer function, multiplied by the integral of our transfer function squared with respect to frequency. So the most common form of white noise that we will see is thermal noise. So generic random motion of electrons in a conductor would be a type of thermal noise. Random movement of atoms in a mass is also considered to be thermal noise. And sure, no problem. And as I said earlier, thermal noise is not truly white noise, okay? So at very high frequencies, typically greater than 80 terahertz, the noise power amplitude is not a constant. That being said, the finite bandwidth of measurement system and even wires are low enough such that at frequencies, measurement systems have a finite bandwidth, and even wires effectively act as filters at frequencies above 100 gigahertz. And from this, thermal noise is effectively white over every frequency that we're physically capable of measuring. Okay. All right. So now let's talk about the other large type of noise that we'll see. This is 1 over F noise. Okay. So 1 over F noise, also known as flicker noise, is inversely proportional to frequency, which is exactly why it's called 1 over F noise. Okay. So in electrical components, it is caused by random trapping and releasing of charge carriers in electrical components. And let me see if I have this here. I got, okay. So before we talk about where it comes from mechanically, let's talk about this a little bit, because this is something that we are going to see quite often, okay? So random trapping and releasing of charge carriers in an electrical component. Do we have any idea on where we might see that phenomenon being prevalent? So any interface between two disparate materials is going to cause that to happen. So consider something like this, okay? Down below this axis, we have crystalline silicon. Above this axis, we have an oxide layer, okay? So beneath the axis, or beneath that horizontal axis, we have effectively a perfect crystalline structure, right? So we have, let's say, an atom here, and an atom here, and an atom here, and an atom here. We'll have some there as well. And between all of these atoms, we have our covalent bonds, which we discussed previously. So here are the covalent bonds. But what about at the surface of our crystal? We don't have those covalent bonds. We have effectively dangling bonds, which are looking for an electron to fill them up. So they will randomly trap and release electrons. Above, we have an amorphous structure, silicon dioxide, which is not nice and ordered. So it can randomly just give electrons, take them back, and all of that kind of stuff. So anytime we see a material interface like that, between a highly ordered structure and even another highly ordered structure that has a different lattice constant, we will see that electrons become randomly trapped and released at that interface. So anytime we grow an oxide on top of a crystal or smush two materials together to form a thermal bimorph, we are going to have 1/F noise because of that disparity between the periodicity of the two materials. Okay. All right. In a mechanical system, 1/F noise is typically attributed to nonlinear forces in crystalline structures in high Q MEMS resonators. So effectively, we have residual stresses because of the fabrication process of a very high quality factor MEMS resonator. We should expect to see 1/F noise as well. Mathematically, we will define 1/F noise as its spectral density V1/F bar is going to be our power spectral density multiplied by the ratio of FC/F, where FC is the corner frequency where our power spectral density Vn squared has equal amplitudes for both white and 1/f noise. So graphically, we would have something like this. So here is F on a logarithmic scale. And then let's do this blue line as white noise. So this bit right here looks like 10 log of our power spectral density. Let's do this red line as our 1/f noise, where we have a simple linear relationship. So this line is 10 log of V 1/f squared. And then this point right here corresponds to our corner frequency. So when those two amplitudes are exactly equal, we hit our corner frequency. Okay. So at very low frequencies, if we have a system where that's suffering from both 1/f noise and white noise, we'll see that at very low frequencies, the 1/f noise is dominant, and at higher frequencies, the white noise is the dominant factor. Right? The RMS value due to 1/f noise, sorry, is, let's see it. I'll write it down as I have it written. I'm not entirely sure here why I have the square of the RMS noise, but I'm going to leave it alone for just a moment. So we have our power spectral density times our corner frequency over our frequency of interest. We're going to integrate this with respect to frequency, where we're going to integrate from some low frequency of interest to some higher frequency of interest. This is going to be equal to our power spectral density times our corner frequency times the natural log of our high frequency over our low frequency. Yeah, I don't see any particular reason why I couldn't put a square root of sine over, or excuse me, a square root sine over everything. So I'll have to investigate if there was a particular reason why I didn't do that in these notes that I made back in 2009. So we'll see. All right. So we've talked about our two most commonly seen power spectral densities. Now let's talk very briefly about the equipartition theorem. So the equipartition theorem of thermodynamics states that the average thermal energy for each degree of freedom in a system is given by W energy is equal to 1/2 Boltzmann's constant multiplied by the temperature. Okay. Yep. So to give you guys a couple of examples of a degree of freedom, a degree of freedom or DOF Neil, do you have a question? Okay. Is defined as a body's ability to store energy, or really have energy, independently of other variables. So, for example, an ideal gas molecule has 3 degrees of freedom. Excuse me. So for each of its velocities in the X, Y, and Z directions, a simple harmonic resonator has 2 degrees of freedom. The velocity of the mass and the displacement of the spring. All right. Good God, that is loud. Yeah. So let's talk about thermal noise in electrical systems. So in an electrical network, the number of degrees of freedom is the number of independent energy storage elements, okay? So I want to be clear about what I mean by that. It's not simply the number of inductors plus the number of capacitors. It has to be inductors that can't be combined with other inductors and capacitors that can't be combined with other capacitors. So if we had, just as a simple example here, this circuit has 1 degree of freedom. because the two capacitors could be combined into a single equivalent capacitance. Whereas this circuit would have 2 degrees of freedom, because there's no way to combine those two capacitors into a single equivalent capacitance because of the presence of that resistor R. Okay, so the left-hand circuit would have a thermal noise of 1/2 kBT. The right-hand circuit would have a thermal noise of simply kBT. Okay, so let's talk briefly here about independent capacitors. So the average thermal energy stored in an independent capacitor is WC is equal to 1/2 C times the square of the RMS voltage, which must be 1/2 kBT. So here I'm simply equating the equipartition theorem, which says an energy storage element is going to have an average thermal energy of 1/2 kBT. And then to that, I'm equating that to the energy stored by a capacitor as a function of the voltage drop across the capacitor. And then we can rearrange this and find that the RMS voltage across a capacitor is simply going to be the square root of Boltzmann's constant times temperature divided by the capacitance C. We can do a similar thing for independent inductors. Where we can say the average thermal energy stored in an independent inductor, which we won't see a whole heck of a lot of, independent is WL is going to be 1/2 L times some RMS current squared will be equal to 1/2 kBT. And from this, we'll have some RMS noise current of the square root of kBT divided by the inductor value. Okay. Now we'll deal with resistances. Okay. So in an electrical system, resistors cause damping of the noise spectrum. The noise spectral density is obtained by associating each resistor. Let me give you guys a moment to catch up so I can go to the next page and continue writing. Am I good to move on? Okay. So we're going to associate each resistor with effectively a white noise generator that provides a power spectral density of Vn squared is equal to 4 kBT multiplied by the resistance value. Now let's look at thermal noise in mechanical systems. Right? So let me draw a terrible picture here of a very simple mechanical system, which is largely what we're going to be dealing with in this class, okay? So let's say that I have some anchor. Over here, I have a large proof mass, M. Connecting my anchor to my mass, I have some spring characterized by its spring constant K. There's no lowercase b, or excuse me, there's no subscript b here, so this is not Boltzmann's constant, yes, because we're about to have places where they both show up in the same expression. Yep, so spring constant because we're dealing with a mechanical system. And then over here, I have a simple mechanical damper characterized by some damping coefficient, gamma. Okay. So we have effectively two essential degrees of freedom that we have to worry about here. The kinetic energy of the mass and the potential energy stored in the spring. Okay, so the kinetic energy portion is as follows: the average thermal energy stored in the mass is equivalent to the classical mechanics definition of kinetic energy. So much like we did with our capacitors, we can say that W kinetic will be equal to 1/2 m v RMS squared. And because we haven't gone through our accelerometer and therefore simple harmonic oscillator descriptions yet. I'm going to go take this one step further. 1/2 m x RMS dot, where x is the displacement of the mass, and so the time derivative of the mass displacement will be the velocity. So just equating things, because we're going to wind up expressing everything in terms of displacement. So displacement will be x, velocity will be x dot, acceleration will be x double dot. Okay. And this is going to be equal to 1/2 kBt. From here, we will have some RMS noise velocity. Yes. Oh, thank you. You're correct. Yes, thank you for that. So the RMS noise velocity of the mass will be given by kBt over m square root. Now, if we look at our spring and our potential energy, the average thermal energy stored in a spring is given by W potential, which will be 1/2 K, our spring constant, times our displacement XRMS quantity squared. This will be equal to 1/2 kBt. From this, we have an RMS noise displacement of our spring that is going to be the square root of kBt over K. Told you guys it was going to get confusing because now we have two different lowercase k's, one representing Boltzmann's constant and the other one representing the spring constant here, and tying these things together. So earlier for electrical systems, we had effectively the energy stored in a capacitor, which is analogous to the energy stored in a mass. Then we had the energy stored in an inductor, which is analogous to the energy stored in a spring. So in our electrical systems, we saw that resistors acted as white noise generators. In a mechanical system, we will see that dampers act like mechanical noise generators, right? So in the event of mechanical damping, we can say that the frequency content of noise in a mechanical system is related to the mechanical damping of the system. The noise spectral density of the system is obtained by modeling the damper as a noise force generator where our noise force spectral density Fn squared will be equal to 4 kBt times gamma. So it's literally the exact same relationship that we see with resistors. All right, we're almost done. How much? Can I go to a new page, or you guys need them? Yep. I'm sorry, what?
How is this your favorite topic?
Did I say noise is my favorite topic? I like it because we don't get to cover it a lot. I also like it because it demonstrates the equivalency between mechanical circuits and electrical circuits. Like, I have been teaching circuits pretty much every quarter for the last 6 years. So that's how my brain is wired to think. So if I get to treat a resonator like a simple RLC circuit, it's much easier for my brain to comprehend what's going on than it is to work in terms of mechanics. I don't know. I don't remember saying that this is my favorite topic in this class. It honestly is, though, just because we're not taking the same, in my opinion, boring old look at everything that we usually do, where everything is ideal, right? We're taking into account the different types of forces and signals that are going to be randomly generated. It also helps us to discuss effectively things like signal integrity and things like we're going to do here, right? So for example, if you have a system that has a lot of damping. So if you took a micromechanical plate that it was affixed to some beams and you didn't put the little holes in it to allow air to effectively escape out, and you subjected that plate to a certain amount of acceleration, which is the full purpose of an accelerometer. Well, it's very likely that the noise force that is effectively generated by your damping system, the fact that there's going to be a pillow or cushion of air between the plate and the substrate, is so large that you can't reliably measure the displacement, because the noise force caused by the air damping is probably larger than the actual force that is going to be generated by the acceleration of that tiny mass. So like, it intuitively helps us figure out how to design better, because we have a reference by which to compare things to, right? If we don't have a signal to noise ratio to look at and say it needs to be higher than this level, we don't know whether or not our design will actually work in the way that it's intended, or if we can actually measure the signals that we're interested in. So like, in a lot of areas, the concept of noise is completely glossed over, but especially in microscopic systems, it is so important to the design and behavior of the devices that you have no guarantee your device will work unless you give it a formal treatment. So, all right, that's me ranting about my odd having favorite nerdy things. So, all right, this is another thing that I actually really enjoy. So this is the concept of input referred noise, and it also goes along with making sure what we are quantifying. Okay, so input referred noise. All right. So I halfway want to go down the hall and get my other notes for when I teach this in the integrated circuits class, because it's a little bit more than half a page of stuff, but I'm not going to make you guys suffer through that. So in most systems, what we're going to wind up doing is referring noise to our input. And so the reason for this is let me think of a simple way to organize everything that I would have talked about for half an hour in another class. If we look at everything at the output, we can't really distinguish what the contribution to the overall noise, the amplifier itself, has, okay? So let's say that we had a simple amplifier like so, with a gain of 100. And actually, let's take that out for now. We observe at our output that we have a noise signal of 10 millivolts, okay? If we effectively don't have anything connected to our input, we're just seeing some RMS noise voltage at the output of approximately 10 millivolts. How does that information help us decide what the minimum signal that we can amplify is? And the short answer is that it doesn't, okay? So instead, we have to wind up referring our noise to the input, right? So let me put a signal voltage here, right? So let's say that I have some signal voltage that is on the order of 10 microvolts. This is my input that I'm trying to put in, and I measure an output voltage of 10 millivolts, okay? I cannot make a differentiation there, and we'll talk about how to make that comparison using a quantity called signal to noise ratio in a moment. But what I can do instead is refer that output noise to the input, which would look something like this, okay? So I have my same amplifier. With a gain A is equal to 100. My output voltage is going to be 10 millivolts, but now I'm going to treat my output voltage as if it were referred to the input. So I'm going to have some quantity here, VRMS in, that is simply my measured output noise voltage as an RMS value divided by my amplifier's gain, which would come out to be 0.1 microvolt. Over here, I have my input signal, which was 10 microvolts. And now I can see that my input signal is effectively 100 times larger than my input referred noise that's being generated by the amplifier. And I should be able to see that I can adequately amplify this signal. So if it were a sinusoid, you'd have a nice clean-ish sinusoid with a little bit of ripple on top due to the noise, as opposed to putting in a sinusoidal signal and getting garbage out because you weren't able to determine whether or not that signal could actually be amplified. Now, I want us to also consider a case of multiple stage amplifiers, okay? So let's say that we have some cascade of amplifier stages where this stage is characterized by some gain A1, which generates some output noise voltage VRMS output 1, and then the output of that particular amplifier stage is fed into a second amplifier stage, like so. VRMS out 2. If we want to refer our noise to our input, how are we going to do that? So the output noise of stage 1 only sees the gain A1. So we're going to have VRMS out 1 divided by A1. I'm going to mess with this in a moment, but we're going to stop for right now. I'm going to leave it as this. And then we're going to have VRMS out 2 divided by A1 and A2, because that output voltage there sees the gain A2 and the gain A1 before we referred it all the way back to the input. So now, make sure I'm going to say this correctly. Do we think that these amplifiers produce correlated noise or uncorrelated noise? So why do you think it would be correlated noise? So correlated means effectively that they're responding to that the cause of the noise is the same phenomenon. But is there any guarantee whatsoever that that is the case here? I would argue no. So what we're going to do is we're going to square everything and then take the square root of the whole thing. So we're going to effectively assume that our noises are uncorrelated unless we're specifically told otherwise, because there's no reason that some amplifier made in process A would have the same reasons for noise as some amplifier made with some other process. And looking at it from the flip side, our output noise, or the noise measured at the output, would be VRMS in scaled by our gain A1, scaled by our gain A2. So we can use this particular setup here. Let's say that we had, well, a simple system like this, actually. Okay, let's just say for the sake of argument that we have exactly 2 amplifiers. If one of them has better noise performance than the other, this equation would help us figure out what order to stage our amplifiers in to get the lowest possible input referred noise so that we could achieve the highest possible signal to noise ratio. All right, so we'll talk about signal to noise ratio now. So signal to noise ratio, or SNR. This is defined as, that does not look correct. Signal power divided by noise power. So the signal to noise ratio, or SNR, is going to be signal power divided by the noise power, or the RMS value of the signal squared divided by the RMS value of the noise squared. More often, we will see this expressed in decibels, where we would have 10 log our powers, which would be the same as 20 log of our voltage ratios. Because our power is equal to voltage squared. So the higher our signal to noise ratio is, the more clearly we can see our true output through all of the noise. So the signal to noise ratio is really just a way to characterize signal quality. And we use this with the input referred noise as a means by which to quantify the noise of the system. Okay, effectively telling us, will our system be able to accurately measure a particular signal or accurately respond to a particular signal? The last thing that I want to talk about here, actually, am I good to go to the next page because I ran out of room here? Yep. All right. Averaging signals, which is a means by which to effectively reduce noise. I misspelled that. Averaging signal. So we can reduce the noise we can reduce the effects of uncorrelated noise in a system by effectively averaging the noise. So the average value of the RMS noise voltage can be given as the square root of VRMS1 plus VRMS2 plus VRMS3, etc., all the way out to VRMSN divided by N is equal to VRMS over the square root of N. So this would be done in a case where you're taking discrete noise measurements, effectively. The signal level needs to be constant during averaging, which limits our measurement bandwidth. And finally, I have a note here that says 1 over F noise cannot be reduced by averaging because the noise power is correlated, not uncorrelated. And this practice only works for uncorrelated noise. All right, so that's the last thing that I wanted to talk about. Just a couple of mentions here. I don't want to say notes because I'm not going to write anything down. I was having computer issues over the weekend, so I was only able to edit 2 of the videos. Apparently, upgrading the program that I use to do it, which is called DaVinci Resolve, upgraded from 16 to 18. And apparently my computer does not much care for 18 at all, because it crashes a lot. So I'm going to try to edit the videos on my computer here, because it doesn't seem to crash when I try to do it. So maybe I will spend the entire weekend and not get just 2 of them done. I need to give you guys homeworks sooner rather than later. So I'm going to try to get 2 of them up this week. One of them will be with respect to the review material. Another one will be noise calculations and stuff like that. My expectation here is that the assignment will be somewhere in the ballpark of 3 to 5 problems, and I'm going to give you roughly a week to do them. So what I mean by that is I'm going to try to get the review problems up hopefully later today, and they might be due on Friday or at some point this weekend. And then the noise problems, I'm going to also try to get up today, but I'm not going to make them due until like next Monday, so that there's plenty of time for you guys to work somewhere between 6 and 10 problems over the next couple of days. The problems that I am putting on the homework set will be very representative of what you should expect to see for the in-class portion of your exams. I am mulling over the idea of allowing you guys to use the exams being closed notes but open homeworks. The only problem with that is it requires me to actually grade your homeworks and return them to you in a timely fashion, which any of you who know me knows that that is not likely to happen. So I'll try to figure something out with regards to the in-class portion of our exam, which we won't actually have that test until after we get back from the break and all that kind of good stuff. I would like to be able to have a homework or two returned to me before I go on break, so that arguably I'll use that time over the break to grade them. We'll see if that happens, but we can all pretend. So anyway. All right, thank you for your time, and I will see you guys on Wednesday when we're going to talk about accelerometers as a simple harmonic oscillator system.